Hello, this is lab number 5. I chose to do the Slinky problem lab, as I will refer to it. It's just one of the recommended ones for the lab number 5. My name is Charlie Romine. Yeah, let's get into it. So introduction. The goals for this lab is to find when the Slinky begins to drop, when the bottom of the Slinky stops being pulled upward by itself, and the whole thing starts to drop, and then to demonstrate static equilibrium, which is what the bottom of the spring experiences throughout the lab. Here's kind of a little preview of the results of my model versus the actual data, but I'll get into that a little bit later. First, physics ideas. Net force equals 0 is a big one for when the bottom of the spring is being still. The bottom of the spring is pulled up while gravity by the rest of the slinky, and gravity is pulling it down, and it just kind of sits until the rest of the spring catches up to it, and then it begins to fall. Also important for all of the labs that we do coding with are the velocity and position update formulas, which are seen there. Those are used for pretty much all of our models. So next we have the initial conditions. We've got the ball in this particular toad is the Slinky. I estimated that to be 0.25 kilograms, as I just looked it up, like what an average Slinky weighs. I didn't have a way to measure the one they used in the YouTube video that I tracked. The video is linked on the page if you want to check it out. And then on the Canvas page, and the initial position, initial velocity, the spring or Slinky starts at rest, doesn't fall at all until it's dropped, and then those are our initial x and y coordinates in meters. Gravity is obviously 9.8 as it always is, and the delta t is 1 divided by 30 because it was recorded in 30 frames per second. So next we've got our computational loops. There's 2 of them. The first one is from time equals 0 to 2.67 when this bottom of the slinky begins to fall. And in there we've got kind of the weight of the slinky, the force of tension, and then the 2, and they should equal 0, the position and velocity update formulas for the bottom part of the slinky. So that runs and plots out our position. And then the next one changes up a little bit for when it begins to actually fall. That value I kind of just found based on looking at my tracker data and kind of seeing where that came out to. So again, we've got the weight, the force, gravity, and just you add those 2 together, and we end up with it moving downward, as you'll see in the next slide. So here are my results as I kind of talked through them. The orange line is the model. The other line is the actual results as tracked through tracker from the video. As you can see, they're pretty close. And then the blue line, which is our actual results, does something a little weird. And I blame that, as we'll see in the next slide, but on the camera only running so fast, and that the Slinky would kind of teleport. So for the longest time, at the bottom, it was dropped, like the top of the Slinky was dropped at our 0-second mark, and then it kind of, the bottom of the Slinky, which is what I was tracking, which is kind of a point mass, was not falling. As you can see, the line's pretty steady. Those little increments are just kind of my tracker clicking being off. And then it starts to fall, but it falls in these like big jumps, and that is because of it kind of teleporting as the frames kind of catch up to the video, if that makes sense. So the error sources are the video only rendering in 30 FPS. And if we go back, we look, these lines, if this was more of a constant slope, would actually be really close. The sort of difference is that my model does not factor in air resistance. I think that's another source of error. The air resistance, I think, could cause that discrepancy as as it's being pushed up actually, and gravity is pushing it down. So yeah, this is a pretty quick lab. So that's basically it. Yeah. Thanks.